Hi, I'm Morgan McGuire from NVIDIA and Williams College, and today I'm going to be talking about the Augmented Artist, computation, and content creation. Historically, the games industry spent a tremendous amount of artist time to produce the detail for the interactive 3D graphics for worlds. Artists would hand paint everything, and they'd hand place thousands of objects and lights. And then wherever the rendering algorithms have artifacts, they would actually redesign scenes and manually adjust the effects to work around those artifacts. And today, artists are increasingly using more sophisticated modeling tools and better renderers. And so where in the past we would spend any amount of artist time to make the image look good, today we're increasingly spending larger amounts of rendering time to make it faster for the artist to get something done. But still, this isn't really closing the gap between what game studios can afford to create economically and what they really want to achieve in these interactive experiences. So in this talk, I'm going to paint some really big ideas about new technology and directions for interactive graphics around the content creation issue. This isn't going to be a particularly coherent pitch. I'm not arguing for a specific direction. What I want to do is share what I've learned recently about the cutting edge of production and research for interactive graphics. And my hope is that by sharing these ideas, we'll collectively be able to ask some really big what-if questions that might inspire long-term research. Now, I'm speaking tonight as sort of a reporter and student of this work, not as an expert. And so I want to begin by acknowledging the real industry experts who taught me about what's going on inside their studios and provide some of the examples that we're going to look at. And I also want to define one term right now so that I can use it casually throughout the talk, which is that when I say artist, I'm using that as a shorthand for any content creator, and there are many different content creation roles within a game studio. Some of these are something like you're painting in Photoshop or with natural media. Some of them 3D modeling or working in level editors, and some are actually operating, say, as an AI scriptwriter at the level of code, but it's not core game code. It's something that's expressing a creative aspect. It's creating the vision of the game. I also want to have you think about a certain perspective, which is that for those of us who are graphics researchers, artists are the people who create the content that communicates our science and engineering results and makes them compelling. So the artists are essentially the ones who make our work look good. It amplifies our results. But for those of us who are game developers, the situation is reversed. Our job is to create the systems that support the artists. And so our job is to make their work as compelling as possible. And of course, ultimately, the role of the researcher should be the same, to advance the state of the art for our tools and runtime systems. I should also point out that a lot of what I'm going to say now applies beyond video games to film and television, and even some other fields like industrial design and architecture. And I'm going to mention some film examples specifically, but I'm going to focus on games, because games are both an economically dominant industry for us, and it's the one with which I have the most personal experience. So let's take this tour of computational graphics. To support a way of modeling that kind of computation for graphics in support of production for games, and let's also make some concrete observation about game techniques. And so in order to do that, I want to point out there's really this crisis going on in the industry. So consumers have this expectation of visual fidelity is going to increase every year. But achieving that quality is going to require more artist time. And so the person years that it takes to create the content for a game has gone up dramatically. And you can see this sort of exponential looking curve based on some real data over time. And what's interesting is that I3D in 2006, Will Wright, then at Maxis, spoke about this problem. And he basically said it was economically unsustainable. The number of artists you needed every year was increasing at a rate that we couldn't possibly make games in the future. And ironically, since 2006, that exponential trend has actually continued. And today there are hundreds of artists on the teams for modern AAA games. And you can even imagine some of the biggest companies approaching the 1,000-person team size, which is really just ridiculous. And when I look at this curve, my first thought is, well, we better all start taking art courses, because by the year 2030, every person on the planet is going to be an artist working on a single game together, and the entire economy of the world is going to be devoted towards creating that game. So obviously there's some kind of a singularity that we're going to approach, because this is not a sustainable model. What's worse, though, for the studios is economically, this problem is exacerbated by the fact that over time, the inflation-adjusted price of a video game has actually fallen. And so if you look across all platforms and all market segments, on average what's happening is games are selling for less than they were previously. And this is good if you're a consumer, but when you have that rising cost of development, this is a serious problem. So we can't just assume that as the experience increases, the consumer will pay more. In fact, what's happening is consumers expect to pay less every year for a higher quality visual experience. And that's what creates this crisis, these two curves overlapping. And this is sort of ironic, right? Because we're now at a time when interactive computer graphics is finally able to start creating some of these really compelling and realistic visual experiences that we've sought for so long. Now, some companies have looked at various strategies to combat this crisis that I would label pretty ineffective. So, for example, you could look at these two curves and you could try to address the problem by creating a worse video game. Or you could try to change the economics, restrict used video game sales, for example, so that you're getting effectively a higher value from every game you sell. You could pay your artists less, that would address the curve. You could pay them exponentially less every year. Or you could release games more frequently, so you could try to leverage existing IP. So none of these are obviously very long-term sustainable models for running a game company. Of course, there are some strategies that have been more successful. Most of these are business strategies, so things like free-to-play and in-game purchases, DLC. You could sell peripherals in addition to your game. And I think there are important open questions going on in the industry about the long-term viability of those, but it doesn't really affect our work as graphics researchers and developers. So I want to set the business aspects aside for the minute, and instead consider some case studies of strategies for addressing this crisis that are relevant to computer graphics research and development. And in order to support looking at those case studies of strategies, I want to step back first and consider the nature of digital content creation more deeply, and really think about what does it mean to create digital content. What is digital art? Well, artists have actually long used computation to increase visual fidelity. Right? There has been math and algorithms, and in this case, it's human computation. Right? So artists have done perspective studies, they've been looking at proportion. There are a lot of ways that you can use algorithmic and computational thinking to enhance art. And obviously around the Renaissance, especially for perspective, this really came strongly into Western art, this notion of using geometry and computation, and even later, closer to the current day with things like Escher and tessellation, but that goes back a long way as well. And I also want you to note that in some of these cases, like mosaics, or weaving, or the tessellations, or this really nice example, so Uccello has this 15th century perspective study of a vase, but obviously with our modern eyes we look at that and say it's 3D graphics, it's wireframe. So these are all cases where what's interesting is there's not just computation, there's computation with discrete elements. Right? So this is moving into a digital realm. It's moving into a place where we can apply discrete math and computer science ideas once we've discretized the problem. And then when you get to the Jacquard loom and some of the earlier French machines from the 18th century, something really interesting happens, which is you actually have these explicit programs and punched cards. And I would argue that this is really the first digital art. So this is artwork. It's visually pleasing. It's communicating visually, but it's discrete and it's being produced by a machine. But a human artist has created the design. And so that's really what I'm going to claim as sort of digital art. And this is sort of the ultimate beginning of the digital content creation problem. Now for the Jacquard loom, the programs on the card are just digital images. They're essentially bitmaps in the modern sense. But the interesting part of the computation that's going on here is still really being done by hand by an artist. And so it's not being done by the machine at that point. So the textile designers worked out and menu-applied algorithms that today we would call things like curve and line rasterization, anti-aliasing, dithering. And there's this really sort of fascinating parallel history of how those later became formalized within computer science by computer graphics, especially in sort of the 50s, 60s, 70s. And today, of course, computational graphics employ much more sophisticated algorithms. But the key differences are not just the image quality that we're getting, from a game like Crysis 3 from Crytek compared to what you would do in a Jacquard Loom. But the interesting thing for us today is that the algorithms are now executed by machines. Right? So not just the creation of the final image, but because we can use machine computation, and comparatively speaking, massive amounts of it compared to what you could do with, say, computing perspective by hand, that's what empowers the artist to create these worlds, and that's what enables the interaction. So let me emphasize that point because it really underlies everything that follows, which is that a digital artist's ultimate and defining tool is not a brush, it's not flesh, it's computation. And that when we have more and better computation, that's what augments an artist's own abilities. That's how you amplify an artist. And so if we would say a paintbrush is an extension of a painter's hand, then a digital artist is really a cyborg who's enabled and augmented and empowered by computation. And this is our salvation. This is the solution to the crisis. We don't need more artists every year to create more and better and increasingly detailed worlds. We need the same artists with more computation. And that is very good because if you'll recall the rising cost curve of game development, I only know 2 resources that can match the pace of that trend. And the first has nothing to do with machines, really. It's the number of players who are online. So there's this human computation aspect that we can leverage. And in fact, a number of games have done that because one of the dirty secrets in the game industry is that the best content that I can add to a game you're playing is your best friend. Right? Another human playing the game with you makes that game compelling, makes that world interesting to be in, even if nothing is going on with the graphics or mechanically in the game at all. And there's some fantastic games like Left 4 Dead 2, World of Warcraft, where the reason people are playing is because they're playing with other people, and the game is enabling that. There are also fantastic games that have good graphics in them, but that's really what makes those games compelling. And of course, the second trend that follows that curve is the rate at which computers have improved. So the number of, say, flops or megabytes that we have available on a machine is going up at this sort of astonishing Moore's law rate. And so in other words, the available human and machine computation resources are ramping up as fast as our development costs and the player's expectation of visual fidelity. And so one solution is that if we can couple artists' productivity to either of those curves, then we can flatten the cost of development. We can make development sustainable because we're hitching our resources to something that's fighting against that cost. And I should also point out that Moore's law, the amount of computation or the number of transistors that you can sell increases exponentially over time. That's an economic law. It's about flops per dollar. And we know that at some point we're going to be able to hit a limit on a single machine, especially something like a tablet or a phone where we have a thermal design limitation. You just can't dissipate more than a certain amount of power, and it's going to take a certain amount of energy in order to flip a bit always. There's some minimums on that, and we're rapidly approaching them. So we know that Moore's law will not continue indefinitely for your phone, say. And we're rapidly approaching that because they're scaling it quickly. But this is an economic law. It's saying what are people willing to pay for? It's not talking about what you can physically build in terms of transistors. And what that means is even when we hit the limit of a local machine, people are still going to be willing to pay more for certain amounts, or to pay the same amount for certain amounts of computation, but those dollars are going to go towards buying cycles maybe on a remote machine. So the computation might not be physically local anymore. And we've already seen this in the web world. So in the sense that the games industry is behind where a lot of the rest of the tech field has gone. And so my big claim today is that the workflow for an artist in 2013 is too similar to that of an artist in 2003. And that we're sort of trying to linearly solve this exponential problem. That's not going to work. And so we need to start thinking about some of these new and exciting ways of getting past that and hitching ourselves to these 2 curves. Now let's take a look at some steps that are already happening in research and real game production to address this. How do you hitch onto these curves? How do you use computation? and speculate about where we might direct our efforts in the near future to solve this crisis. So computational art tools. What are people doing now in the production pipeline? So here's a scene from Uncharted 3. Drake, main character, kind of a Tomb Raider, Indiana Jones kind of guy, is in this scene running down a hallway, and there's this amazing flood of water that's coming behind him. And it has incredible amounts of detail that's being rendered both with an actual mesh of the water's surface, sort of isosurface, and a large number of particles to create all that high-frequency detail. And the way the team at Naughty Dog did this is they actually ran the fluid simulation and building destruction effects throughout the game in usually a film tool called Houdini. So they essentially pre-baked the simulation because they knew exactly where the character was going and how fast they wanted to move him. And then what they're doing is streaming in this dynamic geometry and particles at runtime. So in other words, they used a massive amount of computation to run this fluid simulation rather than having an artist have to deal with placing particle emitters and sort of sculpting what's going to happen with the water. So they saved a tremendous amount of artist's time by spending a large amount of computation. So that's the kind of theme we want to see going forward. And of course, they were targeting a PlayStation 3, which has a fairly old GPU by modern standards. And there was a really nice result, a CA from NVIDIA in 2012, showing that essentially a simulation about that level of complexity you can now do in real time on a very powerful GPU. And so this is sort of another way we might address the artist time problem is instead of using compute resources development time, in some cases you can actually push this onto the player. We're going to use the player's computing resources. We would use their local GPU. And in doing so, we are going to trade some runtime. We're going to lose some efficiency at runtime because there's another effect that we can't render if we're using the GPU for fluid simulation. But in doing so, we again save the artist the time of hand simulating this. And there's a number of tools that will help with this particular problem of physics. Pixelux has a tool called DMM. This is NVIDIA PhysX you're seeing here. There's Havoc as well. Here's another example with Houdini. The mountains and snowboarding tracks in SSX, created with Houdini, procedurally generated, and then artists go in and hand tune them. And also Unreal Engine 4. These mountains, a lot of the detail in the building facades, both in this demo and in games that are being developed on the Unreal Engine 4, tremendous procedural tools. So this idea that an artist can go in and quickly generate a huge amount of detail and then tweak it themselves. We can also look to the film industry for examples, case studies of amplifying artists' effects with computation. So many film production companies right now are moving to physically based renderers from the rendering systems they've used in the past that were sort of expressive and artistically controlled. So for example, Sony Pictures ImageWorks. They produce much of the rendering for films like Cloudy with a Chance of Meatballs that I'm showing here. At one point they moved from Pixar's RenderMan renderer to the Arnold renderer. And one of the major reasons to do this was to save artists time. RenderMan is effect-based. It's a micropolygon rasterizer. So when you want to add a new phenomenon like shadows, reflections, indirect light, you need to add a new mechanism to the renderer, and then you have to tune that. And in order to get reasonable performance, there are also a large number of caches throughout the system that have to be manually refreshed when you've changed something that might affect the shadows, for example. And what's interesting is that's I would say, it's a pretty good description of the state of most game rendering engines today. They're rasterizer, special effect based, and the effects don't all play together particularly well. What they switched to at Sony was the Arnold renderer, their in-house renderer. It's physically based ray tracer. And so when you have new phenomena, they integrate automatically, and it requires many fewer parameters to get an initially robust solution. Then you tweak from there. And Arnold also has the property that handles very large scenes and performs almost all of the effects in camera, so to speak. So it's doing the real simulation. And what they found was that when they switched from RenderMan to Arnold, the Beauty Pass render time increased. They spent a lot more computation to get essentially the same image, but the artist time decreased. And the artist time is what was limiting them. They also found, this is another film, Spider-Man, that was worked on by Sony Pictures ImageWorks, that switching from essentially lots of direct illumination, lots of small lights that artists hand-placed, to true global illumination dramatically reduced the time it took to light their scenes, because they just didn't have as many manually placed lights to deal with. Now, of course, games aren't necessarily going to evolve into whatever films are doing. Interaction is a really big constraint on games. It's the essential constraint. And games have to have a lot more robust simulation than there is in film, because we can't just assume that the shot isn't going to go away that looks bad. Another great example from Sony was that they pointed out, Sony Picture ImageWorks, they pointed out that one of the last people to sort of, the moral equivalent of the post-processing, the screen space effects that we do for real-time rendering, is they have a compositing artist who puts all the layers and special effects together. And in order to avoid stalling the compositing artist, where when he or she went to add some effect and realized, oh, that shot hasn't been rendered yet, I changed my mind, and now I need some different footage, they'll pre-render all the possible shots that they would need, even though most of them are going to end up on the cutting floor, just so that the compositing artist doesn't have to spend their time. Another film company, Pacific Data Images, they worked on many feature films, including Shrek, Madagascar. The one I'm showing here is How to Train Your Dragon. And they have a tool called the PDI Light tool. It's been in use for about 15 years in film production. It has many, many options for quality and performance. And by the way, this is by Lawrence Kesselroot, Drew Olbrich, and Dan Wexler. Won an Academy Award for this system in 2013. This is a well-known, really important lighting system. And even though it has all these options for quality versus performance, Dan Wexler told me that the artist always left it in full quality settings. So they never went down to the low quality preview. And their reason was that they needed to minimize the number of interactions or iterations that it took for them to light the scene. And they were quite happy to get bigger computers and more computers if it reduced the amount of time the artist had to spend. So another example, in production, at development time, spending compute time to save artist time. There is also obviously a lot of great research on this, and this is the kind of thing that I think we need to do more of, especially at i3D. Methods for, in this case, automating camera placement. How do you find places? Can you use computation to place cameras automatically and then let artists tweak them, rather than having artists go through a game and have to place every single viewpoint manually to avoid things like occlusion or confusing viewpoints? And you can imagine systems like this for automating placement of lights. Automatically light the scene, give me some nice three-point lighting, put a hero light on, and then I'll adjust it to communicate what I wanted to as a developer. You could also place many objects, whether they're power-ups for gameplay or merely detail objects. So Bungie was the company that created most of the Halo games, including Halo Reach. And at SIGGRAPH 2009 and 2010, Natalia Tartachuk gave a talk, and she explained that artist iteration time was driving many of their technical decisions, especially around lighting and visibility computation. So they needed to eliminate the really large bake time. So bake is when you pre-compute something. In this case, pre-computing illumination, creating light maps. And they found that the amount of time it took from when an artist pushed a button or moved a light to when they had the result back for the light maps, which in some cases would be hours, was too long. It essentially took too long for artists to get useful feedback, and so it was wasting the artist's time waiting on the computer. And so they moved away from light maps for Halo Reach. So the core technique they've been using for a long time, they had to abandon. And this actually sounds like the opposite of what I've been saying, which is that computation was not the savior in this case. Computation was what was limiting the artist rather than enabling the artist. And there's actually a lot of tension in the game field right now between moving away from pre-computed baked data because there's just this huge latency in adding that to your game, and using more computation and better algorithms to make the baking faster. And so at some point you need to really abandon those pre-computation techniques or really commit to them and really dive into the computation. And we've seen a lot of nice work, and I think we need more of this that's addressing this problem of, well, how can we use the computation we have more efficiently as well as bringing more in? So for example, just today, Lush et al. Showed how to bring down bake times using clustering individual virtual point lights into larger polygonal lights. And they got, for some of these scenes, they're getting down to maybe 30 seconds for a bake time. And so that's the direction that really increases artist productivity. So if we do like the quality of baked lighting, how can we make it faster? Another industry example of staying with baking but pouring computation at the problem, in this case is more brute force, was Remedy. So Alan Wake is a sort of open world horror mystery game, and you're on this large island area, And they used a lot of baking. So they generated this large open world using procedural tools to sort of place lots of trees in the mountains and buildings. And then artists would then adjust that, and they had sort of these biomes that would specify the geometry and textures and vegetation and displacement maps. But what's interesting is they ended up using a huge render farm for that to bake a lot of the data. So both do the procedural data, but then to bake their light maps to bring the artist's iteration time down. So instead of abandoning light maps, they said, we like them, we're going to invest in this a lot. So I hinted earlier, those were all cases where people were doing interesting things at production time, so giving artists bigger and more computers in order to augment them. And what's interesting is there's this other case where historically we've done everything possible to make the game run as fast as possible and squeeze in as many effects, and now that trend is reversing. Where now we're saying, I'm willing to reduce the number of effects or resolution, or maybe even drop from 60 to 30 frames per second, if it means it saves my artist's time. So designing the runtime engine to save artist's time. Bukowski et al. From Vicarious Visions give a really nice talk about this, SIGGRAPH 2012, talking about ways of designing effects that would both degrade gracefully in quality and performance to low-end platforms. So they're working on these Skylanders games, for example, and for these games, they needed to ship on multiple platforms with huge variation in the amount of computing performance on them. And normally what we would do, or historically what you would do, is say, well, on the low-end platform we have sort of low-end art assets, and on the high-end platform we have high-end art assets. And the problem with that is to make the same game run in two places, you essentially double the amount of time it takes the artist. You've doubled the amount of content because you need multiple versions. And so what they did was instead shifted their game development so that they had a single set of assets that were sort of medium quality. They could basically run everywhere. But then make the things that made the final image compelling be effects that could be scaled. So essentially pushing work onto the programmers and onto the GPU at runtime. So they described things like ambient occlusion, depth of field, motion blur, color grading, all these kinds of effects that can be added to the game to enhance what's there without requiring new art assets. And screen space is sort of a wonderful place to do effects like that. So ones that can be layered on after the final image. And creating no new art assets, not interfering with the artist, but enhancing the image. And what's neat is that for many of those, they also have the property that since when you go to a lower-end platform, instead of needing new assets to run faster, you can just simply turn off some of the effects because they're all layered on and composited at the end. And you can also imagine doing things like variable texture resolution to scale, or moving between, say, flat surfaces on the lowest end platform up to normal mapping, and then parallax mapping and the displacement mapping on the highest end GPU. And so this is what they were promoting as this idea of scalable algorithms and assets. So if you have a more powerful platform, the game will look better without making the artist do anything. Here's an example from their talk where they showed the ambient occlusion. You can see, and on the right of the frame, you can see motion blur that's happening to that object. They published all the algorithms in that talk, and they dumped the fields in GPU Pro 4. Natural Selection 2, another example from Unknown Worlds. A case where a very small team, sort of 5-person indie team, trying to create an experience that in some ways is sort of visually comparable to the Aliens movies or Halo, that kind of sci-fi marine look. And one of the things they did was, first of all, they invested in a lot of sort of physics-based effects, heavy shading and lighting effects instead of geometric complexity. So the things that are making this image compelling are not things that take artist time, they're things that take GPU time. And they also found, and this is going to be a theme throughout this talk, 100% automation was bad. So when they created procedural tools that did everything, that was bad because it didn't give them the effects they want. And they sort of target this kind of 90% level. Use procedural tools, use automation to get you very close to the solution, to essentially pre-optimize, and then let the artist really optimize the visual experience because you don't want to take control away. Here's another example from this game. There's aliens that sort of infest these space stations, and when they do so, they create this what's called dynamic infestation. So all of the green stuff, the sort of organic and plant life, sort of mold, rot-looking stuff you're seeing in this scene, is something that's actually layered on at runtime and is created procedurally. And there's a variety of sort of screen space tricks they're using to do that. So all of that's an example of sort of emergent properties and procedural things, in this case at runtime, which is usually something we're a little bit concerned about. They also did a really nice job with automating the pathfinding. So instead of manually placing pathfinding nodes throughout a mesh and then running something like A* to move characters and objects around, that's a very artist-intensive approach. What they did was they created a tool that would automatically build the walkable, or sort of the transport, the pathfinding mesh at edit time, and then insert it back into the level editor and let the designers modify it. So again, that 90% automation, not the 100%. Speaking of pathfinding, we saw a nice talk yesterday at I3D on multi-agent pathfinding simulation. And this is really important for something like an open world like Just Cause or Skyrim. And papers like this one by Golis et al. That advance the state of the art for runtime pathfinding, well, that can really reduce the amount of manual pathfinding and sort of AI scripting that's needed. And so that saves content creator time again. So I think approaches like this are really important. And this is really important research for sort of getting at how can we unlock and augment those artists. This is a shot from Assassin's Creed 3. And what's interesting is Assassin's Creed 3, Far Cry 3, two very different games that are both in production, were in production at the same time at Ubisoft. And I want to contrast the approaches taken with them. So Assassin's Creed 3 was a more traditional kind of an engine. And one thing the programmers noticed is that the artists were desaturating and over-darkening texture maps for the game. This happens to fit the visual style of the game. And so in a sense it's fine, but it's also very visually limiting when artists are intentionally making everything desaturated. And it's going to hurt the precision you have going throughout the shading system if you're desaturated and over-darkened. And what the programmers hypothesized is that the reason that artists were doing this was that they intuitively understood that by desaturating things and making the textures very dark, that reduced the amount of time it was going to take them to lighten texture, because their engine was a nonlinear low dynamic range renderer, so it's a traditional style game renderer, pre-HDR. And so what happens is in that world, the results are much more predictable if you don't have strong colors and really bright textures. And so because the rendering system was not predictable, the artists were essentially modifying what they were doing, their workflow, to make things predictable to require fewer iterations. And they were able to create this amazing looking game as a result, a game whose visual style happens to be compatible with that style. But this is a case where the artists were limited, right? And the artists themselves, their bandwidth is limiting the rate of production and the cost of the game. Now, if you contrast that same studio with Far Cry 3, it's a much more vibrant game. It's using a much more complicated renderer. So this is a sort of a newer next-gen style rendering, HDR. And to use this, the artists had to know a lot more. And they needed even better content to drive that engine, but they couldn't spend more time on it. And so the interesting solution that studio came up with was to invest in consistent and high-quality reference material. So they have this semi-automated automated calibration process for the materials, and they have Munsell color charts, and they're going out and, in some cases under controlled lighting, photographing real surfaces, not just buying texture libraries or downloading pictures off the web. And so with correctly calibrated and sort of physically based materials and lighting, that made the renderer itself more reliable and robust. The artists could trust it, and then they can anticipate the results, and it didn't limit their ability to express powerful visuals. So by investing more computation in the calibration and material capture process at production time, that saved the artist's time. Even though there was an additional runtime cost. It's more expensive on the GPU to run an HDR renderer than an LDR renderer. But if the artist can predict what happens, the production cost goes down. And now Ubisoft is looking at even more sophisticated material capture. They're also looking at going really aggressively into animation, so things like facial performance capture, as ways of giving the artists rich, well-calibrated, usable, predictable data up front rather than creating everything from scratch. And of course, there are other great opportunities in capturing data from the real world and then compressing it to make analytic models. It's a really nice SIGGRAPH paper, 2010, and there's sort of a whole field of BRDF and spatially varying BRDF capture. Here's a paper that shows how to, from photographic references and some calibrated images, compute coefficients, compute analytic models, compute the normal maps directly. So tools like this, again, really important research and sort of a hint at how we might in the future make artists more productive and spend their time effectively rather than just duplicating something we could have measured. And to accomplish something like that, you really need really aggressive amounts of computation just to solve the underlying problem and then to render it at runtime. So some materials, for example, hair and fur, you're not going to be able to just slap a BRDF on this. It's not about the shading, it's that you really need that geometry in there in most cases. So nice paper, Berenger et al., SIGGRAPH Asia, very recent. High quality curve rendering using line sampled visibility. This is essentially, it's solving the brute force problem. You've got all that geometry of the fur, you're not faking it. That's why it looks so good, but not a brute force algorithm, right? A clever algorithm to operate on the massive amounts of data, to use computation, to use data, to avoid having artists having to spend a lot of work to fake a similar effect. Battlefield 3, DICE. This nice talk, GDC 2011, Lighting You Up in Battlefield 3, in which Johan Anderson and others talked about how earlier games by DICE had really huge bake times. So again, lighting, pathing, AI, those kind of things, but especially the light maps. And when they moved to the Frostbite 2 engine that they used for this game, they had much faster iteration because they moved to doing real-time GI on the high-end platforms. So it was an enlightened global illumination tool, and compared to manual lighting and baking, this allowed them to get much faster iteration time for the artists because essentially the lighting was real-time on a high-end platform. They're now heavily investigating other procedural tools and some semi-controlled procedural systems for building out large and detailed worlds. So things like what we were talking about with the Unreal Engine, where you can paint a large set of mountains, they're automatically generated at high detail, and then you can go in and tweak the individual ones you want for a specific scene. The other end of the spectrum from these sort of big AAA titles, something like The Witness. This is from Number None, Jonathan Blow, author of Braid. And so this is a game where you're on an empty island, essentially, and there are these puzzles, you wander around. It's beautifully lit. They have this sort of GPU-enhanced radiosity they do as a pre-computation at a bake time. But here I don't want to talk about the rendering so much as there's another problem they're solving in a really interesting way with computation, which is when you navigate the island, you're walking around, and as I'm sure we've all experienced in interactive systems and in games for many of us, sometimes you're walking around the world and you fall through a hole or you get stuck on a rock. And it's because navigation is a really hard problem. Right? When you have a live physics system running, you have the simulation, any small errors in the underlying mesh can create these unrealistic behaviors. And the way that this team solved it, I think, is really unique and really fascinating. So what you're seeing here is sort of we're looking down at the base of some trees and some grass, and the white overlay that looks like a wireframe is not a wireframe. What that is they wrote a program that essentially puts a player into the world and randomly wanders the world, so effectively doing a random walk around the world. And what those white lines are their edges where this virtual player was standing at some node, one of those intersections, and then chose randomly some nearby node and tried to walk to it. If they made it, then a white line shows up. And if they didn't make it, because there was a collision or they got stuck or they fell through the world, then a red line shows up. And what this enabled them to do is they ran this incredible, essentially played the game exhaustively, walked everywhere you could in every possible way. And then they could look at the mesh that was created by all this computation and quickly identify those red places and say, hey, do we like it that you can't walk? In this case, it's good that you can't walk around those trees, right? Or is it bad that sort of pool in the background that you can't get up onto the edge of it? So rather than trying to have QA, have human time, have artists test, and then manually modifying response, they can exhaustively test the whole world. And so the key idea here for me is that this is an artist tool that's not for synthesis of content, it's for analysis of content. And that's something we very rarely do. Right? Have a machine critique the artist's content. And if you think about it as an engineer, well, programmers have type checkers and automated testing and things that'll help detect flaws, right? That'll statically analyze code. And there are opportunities as a programmer to really pour computation in at development time to guarantee that certain kinds of errors don't exist in your program. And this is doing the same thing for artists. Right? This is essentially a compiler for artists that will do type checking or do error checking. And I think this is really exciting when you think about what would happen if you had resources to pour into tools like this that aren't just those of a single machine, that are sort of disproportionate to what's available on a single machine. And I think it might be really worth building art tools that are computationally intense. And my analogy for this is if you think about you have an Air Force or Navy pilot, so you have this human being who flies airplanes, who's paid, I don't know, $100,000 a year maybe in the US, but they're flying a $1 billion stealth bomber. Right? That what that human pilot does is so important that it is worth spending tremendously more money and resources to give them the best possible tool to empower them. And this is what Remedy and id were doing in their massive art render farms. So Remedy, for example, was the one that was baking out Alan Wake. id I'm going to talk about in a second with Rage is doing something similar. And when you talk about massive render, hundreds or thousands of computers powering an artist, that's an expensive investment. But this is where distributed computing, where cloud computing comes in, because that's an easy way to scale and amortize these tools. So what would happen if artists had tools that essentially gave them 1,000 times as much computing power as they currently do? And then maybe we can amortize that over a whole art team, because they don't all need it at the same second. And then what's really exciting to think about, what can you do with a runtime system like that? And I say human and machines here, not meaning the human artist, but a totally different idea, which is that human computation is something we can exploit. And in fact, this notion of sort of crowdsourcing your computation has already happened for artificial intelligence. So multiplayer games, well, that's where you crowdsource your AI. You farm out the AI to humans. And I'd mentioned games like World of Warcraft or Left 4 Dead, which are engaging because of those other players. So that's using another human as the intelligence for a character. It's effectively leveraging massive computation. Right? We could instead build a really, put 100 GPUs in the machine to try and simulate a human. Or we can just get some other human to do that for free for us. That's a really effective kind of computation. And I showed Journey here. It's a relatively small indie game that is very, very critically successful on PlayStation 3 by that game company. Journey really put the intelligence and humanity back into multiplayer. So one of the problems with multiplayer games is we want to leverage a human being to provide a compelling experience of interacting with a supposedly virtual human. But there's actually too much of that other human there, and the metagame shines through. It becomes about winning the game and playing, and people use modern speech and idioms in the game, and it sort of destroys that immersion in the world you're creating. What Journey does, and nothing in the game even tells you there's multiplayer, as far as you believe when you start the game, and I'm sorry to spoil this for you if you haven't played the game, you're playing a single-player game, and you're this sort of armless, ambiguous character wandering in a desert. And it's about the experience of sort of being alone and on a quest and trying to figure out what to do in the world. But after a while, you will encounter another similar-looking character who most players think is a non-player character. It's an AI. And you can't speak. You have no arms, you have no tools, or no power-ups or weapons. So your only interaction is just sort of walking around each other. And there's this little whistly note that you can play. And because that interactive experience is mediated through that very narrow channel for expression, it passes the Turing test in the opposite direction. Right? You think of this as a really good AI rather than a human being because nothing has tipped you off that you're playing a networked game. So that's human computation at runtime. And beautifully done in this game, done in completely different ways, but also beautifully for other games. I think that's very powerful. That's a great solution for AI. What does that mean for the content creation problem? Well, people have leveraged human computation there as well. Spore was really interesting. This was the game that Will Wright was talking about in his 2006 keynote. It was then in development. It hits content creation problem from many sides. So Spore has within it procedural art tools. So these are used both by the artist and actually by the player in the course of playing the game. And you can see some of them here. We're pasting Mr. Potato Head style pieces onto this character to create our little alien. So it's the procedural tools that also has player created content. And again, it does sort of a sneaky backdoor multiplayer here. So you're playing a single-player game, but in the universe that you're traveling around, exploring planets, discovering aliens like this one, the other planets are populated with content the game has found on other players' machines that they've created and sucked it off things that other players have created and used it to create the aliens in your universe. And there's also a SIGGRAPH paper describing the animation system used here, which is an emergent, a procedural system that at runtime is spending computation. It's an expensive animation system because it dynamically simulates how these characters will move, but that means the artist didn't have to handcraft animation for those characters. And they do a similar thing with textures. So again, spending runtime computation, the thing that's always been this precious, scarce resource, to save the thing that today is the precious, scarce resource, which is our artist. Little Big Planet 2. Beautiful, beautiful game. You play as these sort of little sock puppety things. Heavy use of runtime effects. Great visual style. Uses a lot of computation. They're doing real-time voxelization. They're doing some limited ray tracing within this game even. But it also is doing that crowdsourcing thing. It has explicit user-created content that you can download. Many of the most interesting levels for this game are not the ones that ship with it. They ship to the editor, and they let users fill out and create content for them essentially for free, right? So turn every player in the world into an artist, and that way you'll scale. And there are some other examples of crowdsourcing. So all of these games, you have some form of user-created content. So a large part of the value of this game is something the developer didn't have to create themselves. The last point is Steam. Valve has this PC electronic distribution system for games. How many people buy their PC games now is through Steam. And Steam has this new program called Greenlight. So Steam is this digital storefront. It's an app store for games. And originally it was curated by Valve. And they found they just couldn't scale, right? Games themselves are content for a store. And they couldn't curate the games fast enough and match market trends. So Greenlight is they crowdsourced the curation. They put all of the games that have been submitted, thousands of them, up for vote. Players can vote for them. The ones that get the highest number of votes come out onto the store. And in fact, they're now talking about, Gabe Newell is talking about taking everything about the store and crowdsourcing it so that you could have your own storefront in Steam. So Valve won't even create the storefront, getting the users to create all of the content, again, so that you can scale. So let's set aside the crowdsourcing for a second and talk about those really crazy art tools, cases where you have disproportionate computation. So Rage, game by id Software, was the first of their games where they talked about using this mega texture approach. And the problem is incredibly large, open, detailed, sort of post-apocalyptic world. They needed to reduce the artist time it takes to texture a world like that. So traditionally, artists to texture a world like this will reuse and layer different textures and spend a tremendous amount of time trying to hide the tiling and the seams. And in the Rage Tech engine, what they're able to do is essentially just paint directly on the world, have infinite detail in the world. And they have some procedural development time tools to help fill the world, so you don't have to paint every single rock. You can sort of fill in broad strokes and then adjust where you'd like. But then they have to pack the textures and do various kinds of baking. So what's interesting is for Rage, they have a 300-core render farm just for the artists to create content for this game. So essentially, you can think of that, if there was one artist there, they would be sitting at 300 machines, not one machine. And that's disproportionate computation, right? That's not something you get in your workstation. And what's also interesting is this also has the runtime side, which is that there's essentially a page table for pieces of textures in memory that's in software on the GPU. And they have to stream in textures. And that's very expensive compared to traditional sort of multi-layer texturing. So they're accepting a runtime cost again to reduce the development time. And those two themes of the massive computation and the runtime, paying the runtime cost to save artist time, the dev time, are what we're seeing over and over again. Going back to Ubisoft with Far Cry 3, this is that vibrant HDR game that they just made, similar to Rage. The lighting for this game, there are thousands of light probes. So every 3 or 4 feet, you have a new light probe that's been baked and stuck in the world. That's what all these cubes are, is they're showing you the lighting that's not normally visible at runtime. Tremendous amount of computation. And they also need to be placed, because you sort of don't want to place them inside geometry. You want them to be places where players are going. So they have tremendous offline tools that they're doing this ahead of time. And so these are all examples of tremendous computation, and the place where you get that computation is in the long run going to have to be the cloud. And we've seen for machine-based, true AI, not human AI, the companies like Google and Shazam and Siri, that's how they're doing it. Your iPhone can't really run Siri. It can upload what you say, and then a big cloud processor comes online, does the actual natural language processing, and then ships the answer down to you. And that's what Google has always done for search, and Shazam is doing for music recognition. And it allows you to get these great experiences from local computation that's limited, but where effectively you can have this limitless remote computation, as long as you can make an economically feasible way of deploying that. And remote rendering is the first step towards this. So there are a number of companies have tools like this Project Shield, which is a remote rendering console. That's the whole thing. The controller is the whole game console, because while it's a fully fledged Android device for Android games, you can play any PC game on that little handheld device, because it's really being rendered somewhere else and the final images are being streamed as video to you locally so fast that you don't perceive the latency. And you can imagine driving that with not just a local PC, but something like the server farm pictured here. And there's a huge number of companies involved in this. So these are all companies that have recently announced products or are shipping products in the sort of remote rendering space of what if we just bring the cloud computing resources to graphics by running the game on the server, and then we'll ship the final frames down to the client if we can do it fast enough. And the power of these things is really amazing. So that's Jensen, CEO of NVIDIA, and you see behind him that kind of green refrigerator-looking thing. That's NVIDIA's grid server. It's multiple rack units, and you can put them all together as many as you need. But that thing right there can serve 720 3D games concurrently. That's a tremendous amount of power. Now, this is an important product for a large segment of the industry. But as a researcher, I'm not actually concerned about whether me or the consumer owns their own GPU in their local machine, or whether the GPU is sitting in the ISP. Right? In both cases, you would write the same code. What I'm interested in is when I look at something like that, I say that's an incredible concentration of computational resources. Right? So that server is this essentially massive meta GPU. It's as powerful as 720 mid-range GPUs, and it's been packaged together in a way that makes it easy to virtualize and dynamically distribute that computation over many users. And so what's interesting is to think about the implication of taking all of that computation and then give that kind of graphical computation to a single artist at development time. So that, to me, is where things get really interesting, because that's disproportionate computation, and it's packaged in a way that you could really deploy it today. So an example of what you might do with something like that, this is an example from the recent GTC keynote talk. So what you're seeing is Maya running on the left side of the screen, and on the right side is a rendering. So this is assets from the Transformers movie, and this is the real asset. So you have the true film shaders, and the image on the right is being path traced. And this isn't like the kind of traditional path trace GPU demo that we're used to seeing in the real-time community. These are all of the crazy effects that film guys bring to the table, where they really care about getting the image right, and they're spending tremendous amounts of computation. And in this case, that image on the right is being rendered in real time through grid. 122 GPUs are doing the path tracing on the right to get that in real time. And this is something that might take hours in a traditional system. So imagine what that means for bake times for games, for example. When you start putting 100 or 200 or 700 GPUs onto the bake times, what used to be a 16-hour